So welcome everyone to the Atto Fridays. Our speaker today is Dr. Álvaro Jiménez-Galán. He is a junior group leader at the Material Science Institute of Madrid, and his work focuses on developing theoretical and computational tools that enable ultra-fast manipulation and probing of electronic dynamics in solids with light. He obtained his PhD in 2015 from the Universidad Autónoma de Madrid under the supervision of Professor Luca Argenzi and Professor Fernando Martin. And later on, he moved to Misha Ivanov's group at the Max Born Institute in Berlin. And in 2021, he was awarded a Marie Curie Fellowship, with which he joined Dr. Julio Vampa's group at the National Research Council in Canada. And since 2023, he is a Talento Fellow in the Quantum Dynamics of Materials group at the ICMM CSIC in Madrid, Spain. So as you can see, top pedigree and top results as well. So we are very pleased that he is joining today. The floor is yours. Feel free to start.
No, thank you very much, Carla. And first of all, as I was saying before, so thank you for this invitation, and thank you for all of this work that you're putting in this initiative of the Atto Fridays. So yeah, let me start sharing. Okay, so I hope it's okay. I hope you see my main screen. Do you see it? Yes. Okay. Yeah. So thanks a lot. I am Álvaro Jiménez-Galán. As Carla mentioned, I'm a junior group leader in the newly founded group CUDIMA, Quantum Dynamics of Materials at the Instituto de Ciencias Materiales de Madrid in Spain. And the work that I will present is funded by the Atracción de Talento grant from the Comunidad de Madrid and by the Spanish Ministry of Science, Innovation and Universities through Proyecto de Generación del Conocimiento grant. So in this talk, I will give an overview of the works I have been involved in the last years, where we use attosecond and strong field techniques to manipulate the electronic properties of 2D materials, and in particular, the Valley degree of freedom and band structure topology. But first, I want to briefly introduce the group that I'm a part of at the Instituto de Ciencias Materiales de Madrid. So we are a newly founded group, a young group, made by three tenured scientists, Pablo San Jose, Elsa Prada, and Antonio Picon. So Pablo and Elsa are condensed matter physicists, the experts on superconductivity and Majorana physics. Antonio Picon, you may know, he's an expert on attosecond physics, in particular attosecond transient absorption spectroscopy. And then we are three junior group leaders. So Laura, who you also may know, she's an expert on ultrafast chirality and shaped pulses. Rui Silva, who's my closest collaborator and a great friend, and he's an expert on strong field physics and the development of computational tools to treat laser matter interaction. And then we have 5 PhD students and 1 undergraduate student. So this is a bit of publicity, let's say, because, of course, if you're interested in working with a fun young group doing ultrafast dynamics in solids, please write us. We have some funding and we are happy to support grant applications. So one of the main assets that we have in the group is a code developed by Rui Silva, and to obtain the time-resolved evolution of the reduced density metrics of periodic crystals during their interaction with laser fields. So let me briefly summarize how this code works. So we solve the Liouvillean equation of motion. We include the Hartree and Fock terms and the coherence terms. So rho here is a density matrix. The Hamiltonian includes the periodic crystal Hamiltonian plus the interaction with the electric field in the dipole approximation and in the length gauge. And sigma h and sigma f are the Hartree and Fock self-energies. And gamma and tau are the coherence and relaxation parameters. So the crystal Hamiltonian and the dipole couplings we obtain either from a parametrized tight-binding model or from density functional theory. In particular, we use quantum espresso in combination with Vannier 90 to obtain a basis of maximally localized Vannier orbitals, and you can find the all of the details here in this paper. Since this step of calculating the DFT band structure and Vannierizing is done only once, we can use demanding exchange correlation functionals, such as hybrid functionals, with which we can obtain more accurate band gaps of our solids. Then we take electron-electron correlations into account at the mean field level. So the Fock term is taken as the screened Coulomb potential that can be obtained through GW calculations or modeled. So for example, for 2D materials, one can use a Rytova-Keldysh potential, which has been shown to work great for excitons. The coherence can be introduced in a reciprocal space through dephasing time, T2, as it was initially done to describe high harmonic generation. But alternatively, we can also introduce the coherence in real space, following the recipe pioneered by Graham Brown in this paper. So, and here one defines a so-called coherence length, and coherences between sites that are separated by a distance greater than this coherence length are damped by some complex absorbing potential. So the code then solves the Liouville equation with initial thermodynamic equilibrium of the density matrix in the presence of an electric field with arbitrary temporal profile and strength. And then we can obtain experimental observables such as the high harmonic generation spectrum, the transient absorption spectrum, or momentum resolved time-dependent populations, which can be used for to describe time-resolved RPS experiments. And additionally, we can also compute intra and interband currents, orbital contributions to the current, since we are working in a maximally localized Vannier basis, or time-dependent coherences, which also, as Graham Brown shown in this paper in 1D, they resemble the real space electron trajectories driven by the laser field. Okay, so I will now dive into the main parts of my talk. So first, I will show you a method to fully control coherently the Valley degree of freedom in 2D materials using ultra-short pulses. So this work is a collaboration with the group of Giulio Cerullo at the Politecnico di Milano. So I would like to especially mention Francesco Gucci and Stefano Dal Conte, who were the key drivers of this work, along with Eduardo Molinero in the theory side from the ICMM, and with support of Misha Ivanov, Paulo San Jose, and Rui Silva. So first, let me introduce the concept of valleytronics, which would be used extensively in this talk. So typical 2D semiconductors are arranged in this hexagonal structure. So there are two different atoms in the two different triangular sublattices, so that this system has broken inversion symmetry. And this, in combination with the threefold symmetry, gives rise to circular dichroism at the K and K prime vertices of the Brillouin zone. So a right circular pulse resonant with the band gap will couple exclusively to the K valley, and a left circular pulse will couple exclusively to the K prime valley. A linearly polarized pulse, which is just a superposition of right and left, will of course populate both valleys equally. So these are the optical valley selection rules. They were pioneered more than 10 years ago. And several experiments have now shown that one can achieve almost 100% of valley polarization, which makes this binary valley degree of freedom a promising candidate for information storage or quantum computation, similar to the up and down spin. And this is a very active field of research, but the caveat is that taking advantage of the valley degree of freedom requires manipulating it faster than its lifetime. And unfortunately, actually, fortunately for us, valley decoherence happens on extremely short timescales. They are on the order of 100 femtoseconds at 30, 50 Kelvin. So one has to act on the valley degree of freedom faster than these times of 100 femtoseconds, which is a big challenge. And recently, several strong field methods have been proposed to this end. So on the one hand, the group of Rupert Huber used a combination of an optical circularly polarized pump that creates valley polarization, plus a strong mid-IR field that moves the carrier population from one valley to the other. And this drive is controlled by the subcycle timing of the optical pump and the mid-IR driver. This, for many in the attosecond community, this is a well-known streaking technique, although now in a condensed matter system for valleytronics. The group of Mark Stockman pioneered valley polarization with few-cycle circularly polarized pulses. And later we showed that few-cycle linearly polarized pulses could also produce valley polarization, where the population of each valley can be controlled by the carrier envelope phase of the linearly polarized field. And finally, polarization-tailored pulses, such as the bicircular pulse, can manipulate the band structure topology and therefore also create and manipulate valley population, as I will explain in the second part of my talk. But the problem, or well, the caveat of all of these schemes is that the change of the pump probe time delay here, or the CEP here, or the phase delay between the two pulses here is done sequentially. So one delay setting per experimental shot. So therefore, these schemes actually do not offer sub-femtosecond control because they are limited by the repetition rate of the laser, which is nanosecond at best. So if we take, for example, this graph here in which we see valley asymmetry as a function of the CEP, each of these CEP points, they correspond to different shots of the experiment. So these are limited by the repetition rate of the laser, which, as I said, is around, let's say, at most nanoseconds, which is much slower, much slower than the valley lifetime. So essentially, in each of these points, the valley population has decayed to the ground state. So we start at the ground state in every of these points. So we are not actually acting on the valley degree of freedom here. Now, if we consider, so, well, actually, I have to say that it is true that once the carriers are initialized here at the K valley or the K prime valley, they will be driven by the laser field to the opposite valleys, okay? And this would be really ultra-fast changing of the population from one valley to another. But this switching of the population will be so following the desires of the light wave. So however the light wave is, so this controlled valley switching and requires subcycle control of the light wave. And this is in principle achievable experimentally, but it is extremely challenging and in this case not practical because one would need to design a light wave taking into account deformations of the wave packet in the Bridgman zone due to the strong light field or scattering mechanisms. So while these schemes give us ultra-fast resolution of the valley dynamics, they are not yet practical to be used as a valley switch. Now, if we consider the pseudo-spin block sphere, such that K and K prime are in the poles of the sphere, and in the equator we have the superposition of the two states, then the previous schemes concerned on having the vector going from one state to the other across the poles. But Cilian Ye, Desensung, and Tony Hines showed control of the Bloch sphere in the equator through the optical Stark effect. So they showed not control of the vector around this axis, but around this plane here. And what they did was use a linear pump that excites a coherent superposition of k and k prime states, as I showed you before, and then a near-resonant circularly polarized pulse that stark shifts only one of the valleys. And this creates an energy splitting between the two valleys, and this energy difference induces a phase shift between the two valleys that can be controlled by the time delay between the linear pulse and the off-resonant circularly polarized pulse, such that you can control the phase along the equator. So 3 years ago, we proposed a coherent control method using ultra-short pulses to manipulate the valley population and coherence that is embarrassingly simple, but that I think illustrates nicely fundamental physics in an applied scenario. So let us consider this three-level system in which we have a ground state and two excited states, k and k prime. Sigma minus couples to k prime, sigma plus couples to k. And then we have some decoherence, gamma d, that acts on the off-diagonal elements of the density matrix, and some inter-valley scattering terms that equilibrates the populations between the k and the k prime valleys. So it takes care of the elastic scattering between the valleys. Now, if we shine a linearly polarized pulse, we initialize a coherent superposition of the k and k prime valleys, as I have told you. And now we add a second pulse, which is also linearly polarized, but in the orthogonal direction, and delayed by a time t12. Now, if the pulses overlap and they are phase shifted by pi halves, then great. We just have a trivial circularly polarized pulse that creates valley polarization. If we increase the time delay of the pulses such that they are non-overlapping, then we can still obtain a circularly polarized pulse for a specific frequency, right? And then for that specific frequency, we should obtain valley polarization as long as the delay t12 is shorter than the valley coherence. So as long as we don't lose coherence in our material between these two pulses, we should be able to induce valley polarization at one particular frequency. In fact, the valley polarization at this particular frequency will oscillate between valley polarization at k, no valley polarization at k prime, etc., because we will have effectively at that frequency a linear pulse, an elliptical pulse, circular pulse, opposite circular pulse, etc., as a function of the time delay t12 between these two pulses. And this decay of this oscillating signal gives us direct information on the decoherence time of our system. Measuring the valley decoherence is actually quite challenging due to inhomogeneous broadening. And in fact, I'm only aware of one work that has measured the exciton valley coherence using a 4-wave mixing setup. And here it seems conceptually easy just by using two orthogonally polarized, linearly polarized pulses. But despite this theoretical simplicity, this scheme is challenging. First, because it requires to have an almost isolated energy level with a strong oscillator strength, so that we effectively have this V-type 3-level system. But luckily for in 2D materials, due to the reduced dielectric screening, there are strong Coulomb interactions between the excited electrons and holes, which creates bound electron-hole pairs, or excitons, that have large binding energies and large oscillator strengths. So one example is tungsten disulfide monolayer, in which the exciton binding energy is 0.32 eV. And this measurement shows the linear absorption of WS2 monolayer with a peak at 2.1 eV for 10 Kelvin, or 2 eV for 300 Kelvin, corresponding to the A exciton. So great, we can have an isolated energy level with a strong oscillator strength, and this exciton also is located both at K and K prime. So we effectively have this three-level system in a condensed matter system. And the second challenge of the scheme that I was telling you requires pulses that are much shorter than the decoherence time, which is shorter than 80 femtoseconds, let's say, and with controlling timing and polarization between them. But this is precisely the type of system that recently the group of Giulio Cerullo at the Politecnico di Milano built. So Stefano Dal Conte and Francesco Gucci were able to perform this beautiful experiment where they generate a pair of phase-locked pulses of 80 femtoseconds duration with a temporal separation T12 controlled with attosecond precision. So the pump pulses cover the spectral range of the A exciton of the tungsten disulfide monolayer so that the physics can be modeled with this nice three-level system of before, with this energy difference corresponding to the A exciton frequency of tungsten disulfide. The valley polarization induced by, or not induced, by this pair of pulses is measured through Faraday rotation of a third probe pulse that comes after. Now, for a fixed time delay, T12 between these two pulses, we can indeed achieve a circular pulse at the energy of the exciton such that we measure a strong valley polarization signal. And this is even if the two pulses are non-overlapping in time. And by delaying the time half a cycle later, we can achieve opposite valley polarization. And again, I stress that these pulses are non-overlapping. Now, the decay that we see here, or that we see here, is dependent on the inter-valley scattering. Okay, so it's just equaling the populations of K and K prime due to elastic scattering. And this, we can measure this decay, and it is around 75 femtoseconds at room temperature. All of these experiments are done at room temperature. Now, if we measure the valley polarization signal, not at the fixed time delay T12, but as a function of this T12, we obtain this beautiful oscillation that I was showing you before. So the cross correlation of the pair of pulses is this Gaussian shaded area. So you see that this valley population still oscillates even when the pulses are non-overlapping, showing the persistent coherence in the system long after they're not overlapping. And from the decay of this signal, we can extract the decoherence time, which we find to be 30 femtoseconds at room temperature. And we believe that this is the first measurement of this valley decoherence time at room temperature, and we can see how extremely short it is, right? Before they were measuring, they could measure it at 30 Kelvin, which was around 80, 90 femtoseconds. At room temperature is 30 femtoseconds. So the question is it realistic to manipulate the valley degree of freedom? Because we have to do it faster than these timescales. And let me again reiterate, so in these experiments and in all of the schemes I was showing you before and all of the works that have been done before, even if you see these oscillations, what looks like valley switching and valley manipulation, valley control, this is not really what is happening, because this axis is not real time, right? Each of these times corresponds to different shots in the experiment, so they are limited by the repetition rate of the laser. So we are not really manipulating the valley degree of freedom, since we are always starting in each of these points with the ground state. In order to manipulate the valley degree of freedom, what we must do is take one particular T12 time, fixed time between these two pulses, and quench the signal before it has decayed. And this has not been done yet. And this would really be manipulation of the valley in real time. So Stefano and Francesco pushed to achieve this with another replica of the initial two pulses. So the experiment can control the time delay T12 and T23 between the two replicas. So as before, the first pulse is polarized along x direction, the second one along y, the third along x, the fourth along y. And what can we achieve with this scheme? Well, let us first consider the usual case, ubiquitous case, where the separation between the two pairs of pulses, T23, is much longer than the decoherence time. So it's like if we had two circularly polarized pulses separated by a timescale longer than the decoherence time. So the first two pulses will create valley polarization. Then this valley polarization will just decay on 30 femtoseconds, 50 femtoseconds, whatever. Then the next two pulses come and again create valley polarization. But there is no valley manipulation here. This is the usual scenario and the only one so far. A second scenario is that in which we have no decoherence at all. So in this case, as before, the first pulse creates a linearly polarized pulse, creates a valley superposition starting from the ground state. The second pulse will create effectively a circular pulse. So we create a population in K. So we have valley polarization. And then if we choose T23 such that this pulse is a pi pulse with respect to the first one, then effectively these two guys cancel. And we are left with only one linearly polarized pulse after this one, which again creates equal valley populations. We have again a coherent state, and so this kills the valley polarization. And then the fourth pulse, which by construction of this experiment should be also a pi pulse with respect to the second pulse, will return the population to the ground state. And this is really switching in real time the valley population, but this is kind of an unrealistic scenario because the coherence exists, right? So what does the coherence, so what does the coherence do? So if the coherence plays a role, but still our time, the time of the second pulses is shorter than this decoherence time, we can still have, of course, valley polarization with the second pulse. Then the third pulse can kill this valley polarization. We switch it off. And then the fourth pulse, since it is only partly coherent, it can switch on again the valley polarization. So this would really be a valley population on, off, on switching in real time. And this is precisely what Francesco and Stefano could achieve. So they create valley coherence and polarization with the first pair of pulses. Before this naturally decays, they can switch it off completely, so they can manipulate this valley degree of freedom with the third pulse, and also with the fourth pulse, they can switch it back on again. So this is also, to our knowledge, the first on-off-on switching of valley population in real time. And I stress also that this is done at room temperature. So in the second part, now I will show how strong fields can manipulate the band gap and topology of 2D crystals. So these works are collaborations with the groups of Matthias Kling at SLAC, Jens Bigert at ICFO, Misha Ivanov and Olga Smilnova at the MBI, and Rui Silva at the ICMM in Madrid. And I would especially like to mention Shubhadeep Biswas and Samit Mitra, who drove the experiment at Stanford, and Igor Tyulnev and Julita Poborska, who did the same for the experiments at ICFO. Now, most of the electronic and topological properties of 2D crystals are controlled by their parity and time reversal symmetries. And in 2D semiconductors, the velocity, which is proportional, well, it's essentially related to the current, has two components. The first component is the familiar term where the particle's velocity, so where it is parallel to the particle's momentum. The second component, perpendicular, comes from the broken inversion symmetry of the crystal and the fact that such broken inversion symmetry has a permanent dipole. And this permanent dipole creates a torque when an external electric field is applied. And this torque force is responsible for this orthogonal component of the velocity that in reciprocal space takes the form of a pseudomagnetic field, which is the Berry curvature. So it is nothing more than the dipole induced by this broken inversion symmetry. Now, the band structure is even under both parity and time reversal, and the Berry curvature is odd under parity, is odd under time reversal, but even under parity. 2D semiconductors, as I mentioned at the beginning, are lacking inversion symmetry, but they are time reversal invariant in absence of external magnetic fields or magnetic impurities. So K and K prime have the same energy, but flipped sign of their Berry curvatures. So this is the Berry curvatures of a typical 2D crystal, 2D hexagonal monolayer, where they are pointing in one case towards you and in the other case towards the plane of the screen, out of the plane of the monolayer. Now, if we somehow manage to break the time reversal symmetry of the Hamiltonian, then we are no longer tied to this relation. And this is what Haldane proposed back in 1988 in a very smart but rather artificial way. So he imagined a staggered magnetic potential with the symmetry of the sublattice. And this staggered magnetic field creates a complex second neighbor hopping that breaks time reversal symmetry. So the system then can have a band structure that looks like this with lifted degeneracy of between the K and the K prime valleys, or even equal Berry curvatures at the two valleys, which makes this system topological. And recently, there have been many works from the Ultrafast community showing how one can track this topological phase transition in the Haldane model using high harmonic generation or transient absorption spectroscopy, and these are just some relevant works on this. But the Haldane model still remains largely a toy model, unlikely to be directly physically realizable, and this is a quote by Haldane in his paper. But that said, in 2014, Jotsu and collaborators realized his model in an ultra-cold optical lattice. And in 2020, McIver, in the group of Andrea Cavalieri, managed to create a laser-driven topological Floquet insulator in graphene with circularly polarized light. This was following the prediction by Takashi Oka and Hideo Aoki of Floquet topological insulators. Now, in the following, I will show you evidence of a laser-dressed analog of the Haldane model in a 2D insulator, where the parameters of this model, and therefore the band structure topology, can be controlled on few femtosecond timescales. So, as I said earlier, many of the electronic and topological properties of the crystal come from fundamental symmetry, so spatial parity and the time reversal. So let's then just naively take a field that matches the symmetry of the lattice so that we can manipulate such symmetries in the laser-dressed system. Now, in 2D crystals, matching the symmetry of the sublattice will correspond to this bicircular field made from a combination of a circularly polarized omega field and its counter-rotating second harmonic, which draws this triangular shape in space. So the Lissajous figure of the field has this triangular shape. And the orientation of this Lissajous figure in space can be controlled by the phase delay phi between the omega and the two omega pulses. If we apply this field to a monolayer, to a 2D crystal, we observe valley polarization. So this is, for example, for molybdenum disulfide. And so we can see that there is population imbalance between the K and K prime valleys. So we have valley polarization. And here you can say, okay, of course, you have valley polarization. You have two circularly polarized pulses. And due to the valley selection rules that depend on the helicity of the pulses, we can have population at K or at K prime. But what if I keep the helicities of these two pulses exactly the same? And all I do is just I rotate the trefoil field in space, but keeping the helicities the same. And then I get opposite valley polarization. So this valley polarization is not due to the helicity of the pulses. So we have a method to create valley polarization that is non-resonant. So these are non-resonant pulses, and that it's not relying on the optical valley selection rules. But the cool thing of this is not that you have valley polarization, it's the reason why you have valley polarization. So let's see the physical reason why we get this. Now we know that during the interaction with the strong laser field, the Hamiltonian parameters are modified. So let's start with the tight binding model of a gapped graphene system, where we have first, some on-site energy M, and we have some first neighbor hopping T1, and higher neighbor hoppings are neglected. The field, so in the presence of the strong field, the hoppings get modified according to the Peierls phase substitution, which is equivalent to the Houston basis in a reciprocal space. And we can write this laser-induced hopping as a cycle averaged term plus dynamical corrections to this cycle average. If we only keep the cycle average term, then okay, we get a correction to the first neighbor hopping, and that's it. But if we include some dynamical corrections, and we can include them at lowest order in our perturbation theory, then we can induce second neighbor hoppings through virtual transitions between first neighbors. So if we do this for the case of the bicircular field, what we find is that this laser-induced second neighbor hoppings through virtual transitions between first neighbors are complex, and the imaginary part of this second neighbor hopping can be expressed in this way, where it depends on the phase delay phi between omega and 2 omega, or in other words, on the orientation of the field relative to the lattice. So depending on this orientation of the field relative to the lattice, we would have an imaginary component which will break time reversal symmetry and give us lifted valley degeneracies, like in the case of Haldane, or we will have real second neighbor hoppings, and in this case, we will have equal valley populations. So this is what I show here. So for different orientations of the bicircular pulse relative to the lattice, we can have a band structure which has valley degeneracy, valley minimum, so a minimum band gap at the K prime valley, or a minimum band gap at the K valley. So the laser-dressed system becomes analogous to the topological model of Haldane, but with the band structure controlled by the two-color phase delay phi. So in this movie, I will show the valley populations as a function of the rotation of the bicircular field relative to the lattice, and the effective band structure that I calculate using the laser-induced T2 hopping from the perturbation theory model that I was showing you before. So for this initial orientation, our bicircular field addresses equally the two atoms. So we have valley degeneracy, and therefore equal valley populations at K and K prime. But as we rotate this field relative to the lattice, we see that we get a band gap minimum at K prime or at K, and this translates into valley population at K or valley population at K prime because, of course, we are in the tunneling regime, and we have that tunneling is exponentially sensitive to the band gap. So, of course, we will have valley polarization if the band gap at one of the valleys is reduced. So in this case, valley polarization is a telltale sign of band gap modification. And the group of Matthias Kling at Stanford, and in particular Shubhadeep Viswas and Samit Mitra, performed the following experiment in a monolayer HPN to let's say, test our theoretical predictions. So they shined this bicircular field and rotated it. And as a function of the rotation angle, they measured the valley population imbalance with a linearly polarized probe and a balanced detector. So first, the bicircular field comes, creates some populations in the valleys, and when both valleys are populated equally, then the probe signal does not generate any perpendicular current, because both valleys are populated equally, and therefore, since we have opposite vary curvatures here and here, we will essentially have an effective net zero vary curvature if both valleys are populated equally. So if this field, this probe field comes, then it will generate linearly polarized light. But if we have valley polarization, and therefore we have a non-net zero Berry curvature, when this pulse, linearly polarized pulse comes, we will generate an orthogonal component because we have a Berry curvature, and this will create elliptically polarized light. And the helicity of this light will depend on the valley which is more populated. So by measuring the helicity asymmetry of the signal induced by the probe pulse, which we can define just as sigma minus sigma plus divided by their sum, we can map the valley polarization. And so this is the measured helicity asymmetry as a function of the rotation of the trefoil field in monolayer HPN. And you can see this really nice 120 degree oscillation, right? So at 30 degrees, we observe that the probe produces an optical response with equal components of sigma plus and sigma minus. So we have no valley polarization, and this indeed corresponds to the case where the bicircular field addresses equally the two atoms. And when the field is oriented such that you create some band gap modification, then we induce valley polarization, and we see a maximum here of the helicity or a minimum, etc. So this rotation is exactly what I was showing you before in the video. And also the experiment further confirmed our predictions, showing that as you increase the intensity of the trefoil, the modulation of the asymmetry grows because the band gap is reduced even further. Well, we could also measure the decay of this valley polarization, which induced by the strong field, which lasts for around 60 femtoseconds. So this has more or less a decay rate of around 30 femtoseconds. And so following this idea, the group of Jens Bigert at ICFO looked at this from a different angle by using bulk MOS2. So this material preserves inversion symmetry since it grows as one layer on top of another with a rotation of 180 degrees. So the one photon valley selection rules that I was showing at the beginning don't work here, because for one layer, a right circular pulse will induce population at K, but for the upper layer, it will induce population at K prime. So this effectively will give no valley polarization. But what happens for the bicircular field? For the bicircular field, actually, we have the same valley polarization for the two layers. So we effectively have valley polarization even in inversion symmetric materials. And why is this? Well, because unlike the case of the circular field, these two systems are not related by an inversion. Indeed, only if the bicircular field here is rotated by 180 degrees, these two will be inversion partners. And we know that if we rotate 180 degrees the bicircular pulse, this will change the valley populations. So this shows that even in inversion symmetric materials, for this bicircular field that breaks spatial inversion also, we have valley polarization. And Igor Tyulnev and Julita Povorska at ICFO observed precisely this valley polarization in bulk MOS2, which is inversion symmetric. And in this case, to measure the valley polarization in the experiment, they used an 800 nanometer probe, which is non-collinear with respect to the bicircular pump, and measured the second harmonic signal. And only if both valley populations are, if we have valley polarization, the signal should be present because this is an inversion symmetric system, so the second harmonic signal should be absent if both populations are equal. And this experiment showed precisely a clear second harmonic appearing after the bicircular pulse, and this rotates with a 60-degree periodicity, showing that valley polarization at K, no valley polarization when the field is oriented in this way, valley polarization at K prime, etc. So this experiment showed that also this bicircular pulse can modify the band structure and therefore create valley polarization in inversion symmetric materials. So with this, I would like to conclude. So I have shown you how we can measure the valley coherence, and this was around 30 femtoseconds in room temperature. We believe this is the first measurement of the valley coherence and room temperature, and how we also can create a few femtosecond valley switch, right? Also at room temperature. I have shown you a light wave induced and controlled Haldane model in an insulator, and how we also we can create valley polarization due to band structure modification in inversion symmetric materials. And this is the first time that also with light, with pulsed light, we can create valley polarization in inversion symmetric materials. So I would like to thank all of the people that have contributed essentially to this work, and thank you very much for your attention.
Thank you so much for this talk. Are there questions, comments? Do feel free to write in the Q&A tab or raise your hand. Takes a while on Friday, but I think it was a really impressive talk about what can be done with shaped fields and solids. So do ask. I mean, one question is what next? What would be, in your opinion, the biggest challenge still that you need to face in these systems?
Well, next steps, well, it's for me right now is to see what the effects of excitons have on all of this system, because many of the results I have shown you, in particular, the second part of my talk was without considering excitonic effects, so electron-electron correlations, but they play a big role in 2D crystals. I mean, they're not gonna change the main results, let's say, but they can induce some dynamics that we don't know, and this would be interesting. That's one part. And the other would be trying to understand a bit deeper the decoherence mechanisms. Of course, this would require probably including electron-phonon interactions, which is, okay, it's a bit challenging, but this is what we are thinking about in the future.
Mm-hmm. Yeah, I mean, this is a good point about the coherence, because if you have the coherence, there's interaction with something else.
Mhm.
And I could see that you measured these decoherence times, right?
Yeah, we measured in the experiment, so not in the so in the theory, the coherence is just modeled as a parameter. But in the experiment, of course, they can measure this, and they measure really fast the coherence times for this valley degree of freedom of 30 femtoseconds. So I think that's why I think attosecond science is absolutely great for these types of problems, because we can act on this quantum properties on time scales faster than the coherence. And then one of the reasons why this many of these quantum properties are not being used is precisely because they decohere super fast. So this is the main problem, right? And this is something that I think we can be it can be tackled with attosecond technology.
Absolutely. Absolutely. I agree. And I mean, one thing that occurred to me when you were showing how you can manipulate these bands with light is that in principle you could perform operations, right? By choosing your field, choosing your system. Because I think a big question is also, if first you have to get rid of the coherence, and then you need to be able to perform some operation, create
Right.
some preposition of state or something like that.
Right. So here, what I was showing you is a kind of a valley qubit. Not exactly a valley qubit because we um, so the I mean, we have a three-level system, right? So
Mhm.
it is not exactly a valley qubit. I think we can actually have a valley qubit with some bit slight modification of the scheme. Um, but the challenge is getting another qubit, right? So right now we only have one, and to have some operations, we need the other one. We need at least another one, and it is a challenge, but I think it's a really interesting direction that I think we should explore. But I believe it's challenging. So I'm not claiming here that we can do logic operations on attosecond or femtosecond timescale. I think these are just, I mean, it's just nice physics, like to play, and maybe they can be useful. Um, but so far, it's just, let's say, pure theory.
Okay, I can see people are quiet today, and I'm asking all the questions, but the chair shouldn't ask all the questions. Ah, we have one. Very good. Um, Shazwat Patak. Can valley polarization be achieved in one-dimensional graphene nanoribbons or carbon nanotubes? What are the major challenges towards it and maintaining it?
Um, so anytime that you have broken inversion, you would have valley polarization. Okay, so in graphene, you cannot have valley polarization with circularly polarized pulses. You can have valley polarization in graphene with the bicircular field. This was also a work that we had with collaboration with Gopal Dixit, and we showed that you can indeed have valley polarization in graphene. And the challenges are very similar. So in graphene, uh, you don't have excitons, which are usually more, um, let's say, they have bigger oscillator strength, so they're much better for valleytronics. In graphene, you would have to have some kind of strong field excitation to have valley polarization, unless you have like some broken inversion symmetry by a static electric field or something like this. And then the challenges would be the same, fast decoherence. You need to manipulate this in really ultra fast timescales. So this is why people do all of this type of experiments at ultra cold temperatures. And why using ultra fast lasers, we manage to do this at room temperature.
Okay, so thank you so much. Uh, I had one more question. Just give me 1 minute. I will just write it down.
Yeah, you have another question. And would anybody else like to ask anything? Some days people are quiet, some days people are not. Also on YouTube, if you are a subscriber, you can post a question in the chat and rest assured that I'm going to read it. So if you're watching on YouTube and would like to ask anything, and I know some of you are watching right now on YouTube, just type the questions and the speaker will do his best to reply. People are quiet today.
No, it's because it's a very simple. In the end, the first part is a very simple idea, coherent control, and that's it. I mean, there's there's nothing more than that. And yeah, I guess it's
Yeah, but if you do after you do it, it's easy. But before you do it,
you have to
maybe
have the idea. So you have to have Misha that comes up with the idea.
exactly. So no more questions. Any comments, questions, anything? If you want to raise your hand, go ahead. Otherwise, we're going to close. The weather is amazing in London. I don't know what happened today. Um,
Yeah, I had one more question. Like, while using this value polarization technique, how can we integrate it to like quantum computers? Like, can you explain that part again? I have little doubts in it.
Yeah. So no, I'm not claiming that we have any type of logic operation. So at most, what we are doing is manipulating one Valley qubit. I wouldn't. I don't know if I would even go that. Well, yes, actually, I mean, we are manipulating one Valley qubit. But to make logic operations, to integrate it in a quantum computer, this is a huge step. I mean, we would need at least another qubit, and this we don't have at the moment. There might be some ideas. Maybe we can use another exciton. I don't know. So the 2p exciton or the b exciton or so. Um, but at the moment, what we are doing is manipulating one Valley qubit. But it's already, I think, quite. It was quite challenging, let's say, this because of exactly this fast decoherence times. So it's nice to create a switch of a quantum property that is not electron charge or spin. It's the switch of the Valley.
very impressive indeed. So if there are no further questions, what happens sometimes, you have these people on YouTube, you ask them forever if they have questions, and like when you switch off, then the questions come. So it is very strange, but it is because it's something we are still getting used to it. We are in the process of using the chat for subscribers, but there seems nobody's asking questions. So if there are no questions, we're going to finish the live stream right now. And if you want to chat to our speaker in a more private setting, just hang in there. So for those on YouTube, thank you so much for watching. And also thanks Dr. Jimenez-Galán once more for this really inspiring talk.
Thank you very
And
much.
I hope to see you all in 2 weeks after Easter, in fact, for another speaker in the Atto Fridays. So take care, everyone, and we are going offline.